Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
It's a pleasure to have Rong with us from Microsoft Research New England, where he's currently a postdoc after finishing his PhD at Princeton. Rong is part of a sort of still small community of researchers using tools and ideas from theoretical computer science to understand heuristics and machine learning, and also to design new algorithms in machine learning. And they've really been having an impact in both communities, both in the theory and machine learning communities. And I think one of the admirable things about their line of work is that they're not just sort of studying toy models, but they're really confronting sort of like big ML concepts. For instance, trying to understand even things like deep learning and why it works, or even like what the definition of it is. So with that, let me hand things over to Rong, who will tell us about practical and provable machine learning.
Well, thanks. Thanks for coming, and thanks for inviting me. Today, my talk is about towards practical and provable machine learning. Well, I'm trained as a theoretical computer scientist, but I'm interested in many machine learning problems. These are problems like if we have a lot of documents, maybe we would like to have an algorithm that automatically tell us what are the topics these documents are talking about. Or maybe if we have a large social network, we want to find what are the groups of people that form communities. Or maybe we have a lot of images, and we want to decide what these images are about. So all these problems, when you look at them, they have a common underlying theme in the sense that here the input is always a lot of data, and what we want to do is to find some hidden structure inside the data. For example, the topics are the hidden structures in the documents. The communities are the structures in social networks. So in general, there are many problems where we have a lot of data, and it would be great if we have an algorithm that can automatically find structure inside the data. However, unfortunately, when we look at these problems from a more theoretical point of view, all these problems for finding hidden structures are often NP hard. So does that mean we cannot solve all these problems? Well, that's apparently not true in practice, because topic modeling, which is a common algorithm for solving the first problem, has been applied to a huge volume of Twitter feeds. And when I go to Facebook, it will suggest lists of friends to me, and those are essentially communities. And also maybe 10 years ago, computers cannot decide whether the image is of a cat or a dog. Now, with the help of deep learning, you can just go to this website, upload this image, and it will tell you what animal this is. So apparently, there's a discrepancy between the theory and practice here. In theory, we think all these problems are NP hard. But on the other hand, all these problems are solved to some extent in practice. So why is that? Why are all these problems that we are solving in practice, we think them as NP hard? So to understand that, let's maybe first look at how we formalize these problems in theory. So in machine learning, many of these problems of finding hidden structure is modeled using probabilistic models. So this is a case where our input is a lot of data. And the underlying assumption is the data we have is generated from a probability distribution that can be described using a small number of parameters. So we call this class of probability distributions the model. So given both the data and the model, learning is just a task of finding a good fit to these parameter values, finding the set of parameter values that can best explain the data that I observe. And that's often the NP hard step, because although I said the number of parameters is small, there is still an exponentially large space of possible parameters that we need to search through. And we want to find the best among all these parameters. So does NP hardness prevent us from saying anything about the theoretical guarantees of these problems? Well, the answer is no, and at a very high level, we actually know why that is the case, because NP hardness is a hardness in the worst case notion. When we say a problem is NP hard, for example, maybe we say the topic modeling problem is NP hard. What we mean is there could be an adversary that could generate a bad set of documents. For that particular set of documents, it's really hard for any algorithm to decide what topics they are talking about. But do we really care about those documents? Well, maybe not, because maybe I have just a lot of New York Times articles. And what I really care about is what topics are these New York Times articles talking about? So it is often the case, and that's what I'm trying to convince you in this talk, that by making reasonable assumptions, we can separate these natural instances from the adversarial worst case instances. So, and in the case of natural instances, theory and practice can work very well together. So this is beneficial for both sides. For theory, we can get new problems from machine learning, and we get new perspectives in looking at beyond worst case analysis. For machine learning, we can hope to design new algorithms that have provable guarantees. We know why these algorithms are working, and if they are not working, we know why they fail. We can hope for new algorithms that are better, faster, or more robust. Or at the very least, we can hope to get better intuitions on what kinds of problems are easier and how to reduce harder problems to easier problems. So most of my work has been in that direction of designing algorithms with provable guarantees for machine learning problems. So I've worked on problems like non-active matrix factorization, finding the communities, learning mixture of Gaussians, or certain kind of deep networks. So in some cases, the algorithm we design are actually very efficient in practice. That has been the case for topic models. We have this new algorithm for finding topics in documents that is not only provable in theory, it is also very efficient in practice. So in some other cases, the algorithms that people are using in practice already work reasonably well. In those cases, we can hope to get rigorous analysis of these algorithms that we already use. So that's the case for sparse coding. I will explain what sparse coding in a minute. And you will see why this is a picture for sparse coding. So all these examples are trying to design or analyze algorithms, individual algorithms for individual problems. But in machine learning, there's actually a common phenomena that there are just a few different kinds of meta-algorithms that are tried out in many different applications, like expectation maximization, for an example. So it would be great to eventually have a framework for analyzing these meta-algorithms to decide when they will work and when they will fail. So in that context, I've worked on tensor decomposition algorithms, which we view as a framework for understanding method of moment algorithms. So in this talk, I will mostly focus on our recent work on sparse coding. So we give a simple and practical algorithm for sparse coding. Towards the end, I will briefly discuss my work on topic models and tensor decompositions. So now let me get into sparse coding. So sparse coding, the idea of sparse coding is quite simple. So the idea is we have all these complicated objects. All these objects are built from sparse combinations of much simpler elements. So the hope would be if we have these complicated objects, we want to find out what are these basic elements that we use to build the complicated objects and what are sparse combinations. This is also an example where we show some complicated non-convex function can be optimized by a very simple procedure. So why are we interested in representing complicated objects using sparse combinations? Well, the original motivation came from neuroscience in 1996. So back in 1996, Olshausen and Field, they were trying to understand how our brain interprets natural images. So before them, there were some experiments that show the neurons in our brain, the first level of visual cortex, have these properties. The reactive patterns of these neurons are localized, oriented, and bandpass. So what do I mean by that? What I mean by localized is that a particular neuron will only be sensitive to a very small region in the image. So that's why I'm dividing this image into small patches. And by oriented, what this means is this particular neuron is only going to be activated if that patch has a particular orientation. Think of horizontal or vertical. And finally, bandpass basically means the important feature of this patch, image patch, should be that its color shouldn't change very frequently. So it should be a more low-frequent filter. So one interesting problem is why do the reactive patterns of our neurons have these properties? And a common explanation is that our neurons have these properties because our brain is trying to encode natural images in an optimal way. So our brain is trying to optimize for some objective function. And as a result, the neurons will have these properties. So these are the properties of the solution of that optimization problem. So the problem that Olshausen and Field were interested in is what is this particular optimization problem that our brain is trying to solve? So in order to understand that, they did a few experiments. So the first thing that came to mind when you ask for trying to represent data using some combinations is to run the principal component analysis on natural image patches. PCA is one of the most commonly applied data analysis tools. So this is the first thing they tried. And as you can see, the right-hand side is the result of applying PCA to natural image patches. Apart from the first view, these results are not oriented. They are also not bandpass. So this clearly contradicts with our observations here. So PCA is unlikely to be the problem that our brain is trying to optimize. So what are some other possible options? So another thing that Olshausen and Field tried is to do sparse coding. By that, I mean they try to represent every image patch here as sparse linear combinations of much simpler elements. Usually, we call these elements filters. And when they try to do the sparse coding, these are the images they were able to get. As you can see, all these filters, they are oriented and they are bandpass. So that agrees with what people have observed for the neurons. So they conclude that sparse coding is one of the plausible explanations for the optimization problem that our brain is trying to solve. Of course, there are some other intuitions on why sparse coding is natural in terms of, for example, energy efficiency, but I will not get into those details in this talk. So anyways, sparse coding, as Olshausen and Field observed, is a plausible explanation for how the first layer of our visual cortex is trying to represent natural images. As a result, it has been applied in many image processing applications and also in machine learning. So there are just too many applications to go through. Let me just highlight a few. For example, in image processing, people care about image completion. This is a case where we get this image on the left-hand side. Here, there are a lot of black pixels. All these black pixels are not really black. We know these are the pixels that we don't observe. So all these pixels, we don't know what color they are. The goal of image completion is to fill in the color of these missing pixels in order to get the picture on the right. So in some cases, sparse coding can be very effective for the image completion problem. In particular, in this case, where the missing pixels are random, the left-hand side is actually the input of the algorithm, and the right-hand side image is the result of this image completion algorithm in a paper that uses sparse coding. So as you can see in this particular example, it's very effective. In machine learning, sparse coding is often used as a building block for earlier deep belief networks. It's viewed as a way to do feature learning. So with all these applications, so let's now get into the math. And mathematically, what is the sparse coding problem? Well, sparse coding problem can be thought of as a matrix factorization problem, where we try to factorize this matrix Y into the product of A and X. So what are these matrices? Well, the matrix Y is a matrix of signals. Every column in this matrix Y will be one of the signals that we observe. So think of every column as representing these image patches that we saw before. And what is the assumption on the signals? How are these signals generated? Well, the idea is all these signals are sparse linear combinations of some more basic elements. So in matrix notation, this corresponds to the case where we have matrix A, which we call the dictionary matrix. So this matrix will have n rows and m columns. So every column of this dictionary matrix will be a dictionary element, which is one of the basic elements that we use to build a sparse signal, to build the signal. So think of every column in this dictionary to be one of those edge filters we saw before. And in order to generate a signal, we multiply this dictionary matrix with a column in the matrix X. So X is a matrix of sparse code. Every column of X will have at most k non-zero entries. As a result, if I take the product of this dictionary matrix and this particular column in X, by the rule of matrix multiplication, what I get is a column in my signal matrix. And this particular signal is exactly a sparse linear combination of the dictionary elements. So the problem of sparse coding is just a problem where we have this unknown dictionary matrix A. Every time we generate a sample by first randomly select a sparse code X. And then what we observe is the product of this dictionary matrix A and the sparse code. So everything that we observe are sparse linear combinations of the dictionary elements. Given a lot of these observations, our goal is to find out what is this unknown dictionary matrix and what are these unknown sparse combinations. So So in this case, in fact, this is a problem that's closely related to many classical problems in theory and machine learning. So let me, before going into that, let me first emphasize that the most interesting case for sparse coding is what we call the overcomplete case. This is the case where we have more dictionary elements than their individual dimensions. So in some sense, the dictionary matrix A should be a fat matrix. It has more number of columns than the number of rows. So in this case, dictionary learning or sparse coding is really closely related to a problem called compressed sensing. So the compressed sensing problem is a problem where we are given the dictionary matrix A. We observe a signal Y that is a sparse combination of columns in A. And we would like to know what is this unknown sparse signal X. This is often also called sparse recovery in different contexts. So as you can see, the sparse coding problem is a harder version of compressed sensing because we are not given the dictionary matrix A. We only observe Y, and our goal is to find both A and X. So why is that even possible? Why should I expect the solution to be unique or reasonable? Well, it really has to do with the sparsity in the matrix X. And indeed, the problem will become much harder when the sparsity of X become larger and larger, or the number of non-zero entries in X become larger and larger. So when the number of non-zero entries in X, in every column of X, is just 1, then this is really just a classical clustering problem. Because if every column of X has only one non-zero entry, then we know every column in Y will be exactly equivalent to one of the dictionary elements up to scaling. So in that sense, this is just a clustering problem. When the sparsity is much larger, the problem becomes much more flexible. And when the sparsity is as large as the dimension of the dictionary elements, then the problem becomes impossible to solve because if my matrix A has full rank, no matter what signal Y you have, I can always find a vector X that has at most n non-zero entries such that A times X is exactly equal to your signal. So in some sense, there are just infinitely many trivial solutions, and there's just no way for us to tell which one of them is the solution that we would like to find. So when the sparsity is between 1 and n, the problem could potentially still be possible, and it becomes harder and harder as we get closer to the limit. So in the previous work with Sanjeev Arora and Ankur Moitra, we gave the first polynomial time algorithm for this overcomplete sparse coding problem. And our algorithm can handle sparsity almost up to square root n, which is a natural limit in this context. So in this talk, I'm going to actually talk about a more recent result where we show not only there is a polynomial time algorithm, in fact, the algorithm that people use in practice is better. And we can show a variant of the very original algorithm used by Olshausen and Field will always converge to the correct solution. So in order to seize that result, let's first understand how Olshausen and Field tried to solve this problem. So Olshausen and Field were trying to find the sparse linear combinations that represent the signals. So how do we do that? A natural idea is let's try to optimize some objective function. And hopefully this objective function would say, would capture our desired properties of the problem. So they decided to optimize this objective function, which has two terms. So the first term is an arrow term. It says my signal should be close to my representation a times x. So that is very natural. And the second term will be a penalty term that encourages sparsity of the solution. So this is a term that only depends on the sparse code matrix X, and it will be large if X is not sparse, and it will be small if X is sparse. So hopefully when we optimize the sum of these two terms, eventually we get a solution that's both accurate because of the first term and also sparse because of the second term. So that's nice, but there is a problem here. So the problem is this objective function that we are trying to optimize is not a convex objective function. It is non-convex because here we have both a and x as unknown variables. And it's just because of this first term is already non-convex. So how do we optimize this non-convex function? Because in general, we don't know how to find the global optimal of a non-convex function. So the way Olshausen and Field tried to do this is to first, let's try to make a guess on what is the dictionary matrix A. Well, suppose we already know the dictionary matrix A, we can fix the variables A in this formula and try to optimize for X. In that case, the whole problem becomes a convex optimization problem, which we can solve efficiently. Is there a question? So based on our initial guess on dictionary A, we can find the optimal sparse code with respect to this dictionary. Now with this sparse code, we can fix this variable x in this function and then try to find a better dictionary A. There are multiple ways on how to find a better dictionary A. The way Olshausen and Field tried is to take a gradient step with respect to A. And then hopefully now we have a better idea on what the dictionary is, and we can repeat this procedure to try to get better and better dictionaries and sparse codes. And eventually the hope would be this will converge to a solution that optimizes this function. Okay, so this is a very nice algorithm in practice, but there is still the problem. Why can this very simple alternating algorithm find the global optimal of this non-convex function? In fact, this is a very general idea for optimizing these kind of functions. We can try to optimize different sets of variables alternatively. And that's usually known as alternating minimization. Why can this alternating minimization algorithm optimize this non-convex function? So people have tried many things to try to understand this phenomena and design better algorithms. So in practice, almost all the algorithms used for sparse coding are based on these alternating algorithms. These algorithms differ in the way they optimize over the sparse code and the dictionary matrix A. And in order to justify these algorithms, at first people were only able to prove local analysis. By local analysis, I mean these are kind of results that says maybe it's very hard to understand why the algorithms should converge globally, but at least let's make sure that suppose the algorithms start at a point that's very close to the global optimal, the algorithm should not, the alternating steps should not make this solution go away. It should really converge to the optimal if you start really, really close. So even these local analyses were quite non-trivial. And only until very recently, people were able to design provable algorithms for these sparse coding problems. And these provable algorithms are usually very different algorithms from the alternating methods. If you are familiar, there are some algorithms, including my previous work, that does have an alternating minimization step in the algorithm. But those arguments only start to make sense when we already have a really, really nice solution, when our solution is already super close to the optimal solution. So it's only also along the lines of local analysis, those parts. So the results that I'm going to talk about in this talk can be viewed as a way to combine all these three lines of work. In this talk, we show the alternating minimization algorithm will probably converge to the global optimal solution in a very large radius. So this radius is going to be so large that it's actually very easy to get an initial solution that's within this radius. So once we get that initial solution, we can just do alternating minimization and make sure we converge to the global optimal. Of course, in order to get this kind of guarantees, we need to make assumptions. Even these local analyses that I mentioned before, they require properties of the problems. Without any assumptions, even the sparse recovery or compressed sensing problem is NP-hard. So really, we are trying to make some assumption on the dictionary matrix. And the problem is, what should we assume? What kind of dictionaries are reasonable? So let's consider this simple example. So here is an example of a dictionary. It has 4 elements. These are 4 image patches. All the image patches that we observe should be a sparse linear combination of these dictionary elements. So now, suppose we observe this image on the right, except we don't observe the pixel in the middle. So based on this dictionary, and the problem is that what we observe should be a sparse linear combination of the dictionary elements, one thing we might want to do is to tell what is the color of this missing pixel. That's actually a toy version of the image completion problem that I just mentioned. And as you could see, in many cases, sparse coding is actually effective against this kind of problems. So surely for this very easy toy problem, we should be able to say something. So in this case, what is the color of the missing pixel? Well, so in this case, if you just think about it for a little bit, the answer is I have no idea what is the color of the missing pixel. Because if it's a combination of, say, those two, then it should be green. If it's a combination of the third one, or these two, the color should be red. Question?
I say it's white. Because there's 2 dictionary entries voting white. And only one each for red.
Yes. Yeah, there are many actually 4 possibilities in this toy example. Yes. So. Oh, right. Yeah. So in this case, the point is we really don't know what is the color of this missing pixel. And that is really bad, right? Because we want to apply the sparse coding algorithm to applications like image completion. But if the dictionary that I eventually learned cannot solve this toy image completion problem, there must be something that's not good. And what have we learned from this example? Why can't we decide what is the color of this pixel? Well, one thing that we observe is this uncertainty is happening because, in some sense, the sparse representation is not robust at all. In the image on the right-hand side, I can just, suppose I know the color of this pixel, I can just change the color of this pixel, say from red to green, and my sparse combination would suddenly switch from using those 2 dictionary elements to using another 2 dictionary elements. So I just changed a single pixel in my image, but somehow my sparse representation, the support of my sparse representation changed completely. So this kind of non-robustness is something that's really problematic. So one idea is maybe to prevent this from happening, let's make sure the sparse representation for images should be unique and robust. By robust, I just mean if I change a small number of pixels, at least what dictionary elements I'm using to represent this image should be stable. So what are the kind of dictionaries where we can make sure the representation is unique and robust? Luckily, that's a well-studied problem in the compressed sensing literature. Recall that this is the problem where we are given the dictionary matrix A. We are also given a signal Y that is a sparse combination of the dictionary elements. And we want to know what is this sparse code X such that AX is equal to Y. And we are looking for properties of the dictionary matrix A that will allow X to be unique and robust. So there are many sufficient conditions that we know where this is possible. There's really a long line of work here, so I cannot go into all the details. And I will only mention the ones that are related to this talk. So there's a very nice condition called the incoherence assumption that's sufficient for getting a unique and robust representation X. What that says is ideally, in order for X to be as robust as possible, if A is, say, an identity matrix or an orthogonal matrix, then it'd be great. It'd be very easy to invert A and get a very stable X. But that's not going to happen because we have more dictionary elements than the dimensions. Not all of the column vectors can be orthogonal to each other. So instead, let's make sure that although they are not orthogonal, they are very close to orthogonal. So let's make sure dictionary elements have inner products bounded by mu over square root n. Recall, think of these columns as unit vectors, and n was the dimension of the dictionary elements, and think of mu as something small, either a constant or maybe log. So when this property is satisfied, what we can guarantee is whenever the number of non-zero entries in X is at most square root n over 2 mu, the solution to Y is equal to A times X is unique and robust. And further, there are efficient algorithms that can tell what is this sparse code X. As I said, there's really a long line of work. There's many things before the incoherence assumption and many other assumptions that came after and are much weaker. But in this talk, I will just focus on the incoherence assumption. So under this incoherence assumption, we can hope to prove that there is a guaranteed algorithm for sparse coding that's very similar to the original algorithm of Olshausen and Field. In particular, when the sparsity, when the number of non-zero entries in X is at most square root n over mu log n, we show two things. We first show there's a simple algorithm that will give us an initial dictionary A that is column-wise quite close to the true dictionary. And by quite close, I mean their distance is 1 over log n. So they are somewhat close, but not as close as we hoped for. Especially all the previous algorithms require these things to be 1 over n or 1 over k close. So even though our initial guess on the dictionary is not very accurate, we show a variant of the Olshausen and Field update rule will converge to the true dictionary at a geometric rate. By geometric rate, I mean after every iteration of this finding better X and finding better A, the distance to the optimal solution will shrink by a constant factor. And also notice that our requirement is the sparsity can be at most square root n over mu log n. That is almost optimal because even if we knew the dictionary matrix, even if I give this dictionary matrix A to you and ask you to just find the sparse code X, we would need the sparsity to be square root n over 2 mu, so we are only a log factor away from that. Yes?
Okay, good. So I've always been concerned a little bit about this incoherence assumption setting because in real life dictionaries, let's say, you normally are going to have correlated features which are going to have more than the square root of n dot product associated with them. And in your case, you're actually learning the dictionary yourself. So I'm still kind of confused in terms of how does that assumption impact you directly?
I see. Right. So the question was, in practice, is it reasonable to assume the incoherence assumption? Is that what you are?
I think in practice is not reasonable.
Right. So it, well, arguably that's true. And so first, I think this is a starting point for understanding these alternating minimization algorithms. And we actually did try these kind of algorithms on natural images in practice. And indeed, as you said, the strict incoherence assumption is not satisfied there. What we actually observed is there's an average version of incoherence assumption that's reasonable in practice. So that version says most of the vectors have very small inner products, but they do allow a small number of pairs to have large inner products. And we observed that's reasonable in practice. Our results can actually be modified to also work in that case, but the proof is a bit more complicated. So does that answer? Yeah, thanks. Yeah, so we've actually experimented this algorithm in practice, and so here's a plot or a illustration for the performance of these kind of algorithms. For all these alternating algorithms, in this plot, this direction is the number of iterations we iterate between this optimizing x and a. In this direction is the log of the accuracy. For all these algorithms, the speed of convergence is quite slow at the beginning. And after some point in time, they could go in two directions. So if we are lucky, the algorithms could converge to the optimal solution quite efficiently. But if we are unlucky, they can also get stuck at some bad points and does not really get to the global optimum. So our result basically shows two things. One is, suppose we are already lucky, suppose we have a good initial point, then this kind of update rule that looks like all-Southern and field algorithm will converge geometrically to the global optimal solution. And secondly, we also give this simple initialization algorithm that's going to guarantee we start from this good initial point. So we are never going to go along that path and get stuck. And we can also get around this slow phase in the beginning. So in this talk, I'm going to mostly focus on this part where we show, suppose we have a good initial point, this kind of update rule will converge geometrically from this nice initial point. So how can we hope? Right, so the initialization algorithm is a spectral-based algorithm. We just pick random samples and pick samples that are correlated and do some spectral algorithm on top of that. I can explain in more detail if we have time afterwards. Right, so yeah, but in the talk, I'm mostly going to focus on the second part. So how can we hope to show that these kind of algorithms converge to the global optimum? Well, remember the algorithm we are trying to analyze is trying to optimize this objective function. And we don't really know how to analyze this because, in particular, this objective function is not convex. So how do we try to analyze this non-convex function? A natural idea is maybe we can relate this non-convex function to a convex function. And there's actually a natural candidate. We can let g of a to be the function of f of a and x star. And here x star is the optimal sparse code. It's the sparse code that we used to generate the samples. So if we fix the optimal sparse code x star, then as you can see, this function of g just becomes a quadratic function on the dictionary matrix A. So it is a convex function, and it's also easy to see the optimal point of g is the same as optimal point of f. So now we actually have two choices. We can try to analyze this non-convex function, or maybe we can try to analyze the convex function g of a. But the only problem is we don't know how to compute g of a because we don't have access to the optimal sparse code. So the hope would be these two functions are actually closely related because we have a reasonable initial guess for the dictionary matrix A. So hopefully the sparse code X we generated from this initial dictionary matrix A is close enough to the optimal sparse code X star. So the partial derivative of f with respect to A is very close to the gradient of g. And because we always converge if we follow the gradient of g, we can hope if we follow the gradient of f, we are also fine. So we call this idea the idea of approximate gradient descent. And the main problem here is we need to specify what do I mean by the gradient of f is close to the gradient of A. So let me reinterpret this approximate gradient framework. So the idea is there is an unknown optimal solution z star that we are trying to find. There is a function g of z that, so if we follow the gradient of g, we will always converge to z star. Unfortunately, we don't have access to gradient of g. We only have access to gradient of f. And we make a step towards the gradient of f. The hope would be, so the gradient of f is not very far from the gradient of g. So by following that, we are also making progress. And eventually, hopefully, we will converge. Formally, we would say the gradient of f is epsilon biased. If this formula is satisfied, it might seem very complicated, but you can ignore this formula, except the important point is in this formula, if I have gradient of g instead of gradient of f, then the same thing will hold, except we don't have this minus epsilon term at the end. So what we mean by epsilon biased is just the same thing that was true for gradient of g is also true for gradient of f, except we have an extra minus epsilon term. And by having this term, we can show if gradient of f is always epsilon biased, after a small number of steps, the distance to the optimal solution is going to be bounded by the sum of two terms. So the first term will be decreasing geometrically, and the second term will not go to 0, and we call that a systematic bias. So basically, if epsilon goes to 0, we can still hope the point to converge to z star. Otherwise, we can only hope the point to converge to a point that's very close to z star instead of being exactly at z star. So following this framework, right, so I chose to use these letters to agree with some standard notations in optimization. So sorry, one problem is this mu is not the incoherence parameter. It is the strong convexity parameter of G, and L is the smoothness parameter of G. Sorry for the overload. So yeah, so these are some standard constants that appear in convex optimization. Right, so under these assumptions, if we just want to show this algorithm converge to Z star or converge to the a point that's very close to Z star, all we need to show is that the gradient of of f is epsilon biased for as small an epsilon as we can. So how do we apply this framework to our sparse coding problem? Well, recall that, so there are some problems because recall that in Osa-Sandon field, we find this optimal sparse code X by solving this convex optimization problem. This problem is well behaved, and people were able to analyze this if A has some nice properties, if A has, for example, the incoherence assumption that we were assuming. But the problem is we were assuming the incoherence assumption on the true dictionary A, but our initial guess is not close enough to maintain this incoherence property. So in general, this optimization problem can be quite non-robust for our initial dictionary. So what we do instead is we use a much simpler decoder, which looks at the correlation of our signals and our current guess for the dictionary elements. Let me not get into detail. The idea is just using this very simple procedure, we can still get a reasonable sparse code that's more robust. And the key lemma we show is using even this very simple decoder, we can show the gradient of f is very close to the correct direction plus a very small bias. This bias is so small, this bias will be the epsilon term in the last slide. This epsilon will be so small that it guarantees the algorithm to converge to a solution where the column-wise arrow for the dictionary is order k over n. So recall we started with a solution that's 1 over log n close. Now we get a much closer solution with k over n. And really, we shouldn't think of this argument as just trying to analyze this one variant of the algorithm. It's a framework that can be applied to many different variants of these algorithms in many different situations. For example, in this simplest case, we didn't consider noise in the model. But if you have noise in the model, it only influences this small bias term, and we can characterize how it influences the bias term and how it changes the column-wise arrow. If we have outliers, if we have samples that cannot be represented using sparse linear combinations, then that also only contributes to the bias term. If we don't have many outliers, the same result will still hold. And perhaps more interestingly, so for this result, we used a very simple decoder algorithm. We can actually hope to use a better decoder to make the bias term go to 0. So really, this is a framework for analyzing many different kinds of algorithms. And in this case, we hope gradient descent algorithm work because the gradient we have approximates the gradient of an unknown convex function. It's an open problem on how to apply this framework to more problems. So let me switch gears and tell you a bit about topic modeling. So for topic modeling, the idea is by making reasonable assumptions, we can find much faster algorithms. Topic modeling problem, if you are familiar, mathematically, is just a different matrix factorization problem. So this matrix factorization problem, unfortunately, is NP-hard. So in order to solve this problem, we make a new assumption, which we call the anchor word assumption, that basically says every topic is a set of words. And for these set of words, we want to know that for each topic, there is a word that appears in this topic and does not appear in any other topic. So once we assume this new assumption, we can actually design many new algorithms that work for this problem. We did many experiments to show that our new algorithm is not only guaranteed to find the correct solution, but it's also much faster than some previous algorithms. And we can also empirically check that our assumption is quite valid in real-life instances. I will just skip this. So just to conclude, in this talk, what we saw is by making reasonable assumptions, we can make machine learning problems tractable. And also, we've seen even very simple procedure like gradient descent on non-convex functions can probably optimize these complicated functions. These are points that occur many times in my research. We can make many different assumptions for many different models. We can also analyze many different algorithms for non-convex functions. So going forward, there are still many open problems in machine learning. I've talked about sparse coding, which is a low-level representation for images, but images have much higher level features. I've talked about topic models very briefly, but there are many other problems in natural languages that are very interesting. Even in applications of machine learning, like computational biology, it would benefit from provable algorithms. And finally, of course, for analyzing the meta algorithms, there are still many open problems in our tensor decomposition framework. And eventually, we want to understand what are cases where we can probably guarantee simple algorithms to optimize non-convex functions. So thanks.
All right.
Main applications of sparse coding these days is as a building block for deep learning.
Yes.
Do you have anything to say about deep learning based on your results?
Right. Sparse coding, so it's mostly directly used in the earlier versions of the deep learning. So in the modern version, it's no longer used as a building block. Empirically, what we did try to use sparse coding in the deep learning framework, what we empirically observe is if you replace the first layer of this deep neural network with the features you learned from the sparse coding, then the performance of the whole network can stay the same. So in some sense, the first layer of this multi-layer structure in deep learning is doing something that's very similar to sparse coding. We don't have a similar result for the second layer. So if you repeat doing sparse coding, it doesn't work. And that's a very interesting open problem that I hope to work on.
Any more questions? All right, let's thank Rong again.